Welcome to Organic Chemistry. I'm really zoomed in at the moment because I couldn't get my video to work. Trying to improve things all the time. What we're doing now is electrophilic addition reactions continued, because there is a bit more information that we didn't cover last time. So we're going to attack with a double bond to an electrophile, or an electrophile is going to come along and attack the electron density inside the double bond, and then we will end up with some products. Typically it will be an addition reaction, but sometimes it's more complicated than that. So we'll come across to me, and then what I'm going to do is go onto a computer background, because then we can see what's going on in a better way. Okay, so back to me. I'm now up in the corner up here, and I will be looking down a bit because I'm looking at my screen. It might look a bit weird to you. Unfortunately, that's the best I can do today. Let's go all the way back up to the top. Oh, no. Back one thing. So you can see I've already recorded this and it didn't work. What we're interested in today is the selectivity of alkene addition reactions. And the first topic is syn versus anti, so on the same side, which would be syn, versus anti, which would be on the opposite side. If we take an example, that will be hydrogen bromide, this one here. If we add hydrogen bromide, we end up with, sometimes we get both of them adding on the top, which would be this one, the syn products. They've both added on the bottom in that case. Or we get, on other occasions, one adding from the top and one adding from the bottom. This makes sense from our logic from before of our SN1 and SN2 reactions. This is the reverse version of an SN1 reaction. So we attack with our double bond to the H plus of our HBr. So it attacks the HBr, causes Br minus to leave. That means that at one end of this double bond, depending on which way it's opened, there will be a positive charge. The carbocation can be attacked by the bromide anion from either the top or the bottom because it's flat. It doesn't make any difference in this particular molecule which end the hydrogen attacks at. We'll come on to that later. And it doesn't make any difference in this particular molecule which side the bromide attacks from, because when it's a carbocation, it's a planar, three flat, even structure, and then it can be attacked from either side. It makes no difference. Because the nearest other bond is right over here, there's very little effect on which side it attacks from. If we go down to another example, we've got Br2 attacking, and what we find is that it always gives anti-addition, meaning one of the bromide ends up on one side, one of the bromines end up on one side, and one of the bromines ends up on the other side. We never see the two bromines on the same side. That's interesting, and it suggests that there is a different mechanism. The different mechanism, while we're on this, it doesn't say it here, is that the bromine molecule comes in from one side and forms a triangular bond. So it forms a bond to both carbons right in the middle of the double bond. That is a structure that is very similar to an epoxide. That would be with an oxygen in the middle, and it's formed in much the same way. And it will then be attacked by the bromide anion, and that is like an SN2 reaction. It can only be from behind, and because the bromine is blocking both of the top sides, it can only come from the back from one or the other side. Because they're both bromines, we can't see a difference, and so it makes no difference which end attacks. Then we end up with always one on the top and one on the bottom. In this case, because it's flat to start with, it's simple-ish, we always end up with one up methyl group and one down methyl group. In this case, one up bromine and one down bromine. Obviously, if this molecule wasn't symmetrical, then we would get a lot more products, but in this case, they've chosen deliberately a simple example. Oops. The scrolling is a little bit awkward here. So scrolling down, we've got another possibility, which is exactly the opposite. It always attacks from the same side in palladium hydrogen attack. So it's catalyzed addition of hydrogen across the double bond, and that is always going to happen on the same side we will have to look at that later. So what we can see is that there are a variety of differences. We can either attack only from opposite sides, or only from the same side, or from both. Going to the next page without stopping, we can see this thing called Markovnikov Addition. Markovnikov is a person's name, obviously, and it's the name of a rule that says if we add hydrogen and something else to an alkene, then we will typically end up with the hydrogen on one of the carbons, and we can decide which one that is going to be. It's going to most often be on one of them. So this is saying what's the most common pattern. So let's have a look, see what it is. If we add hydrochloric acid, in this case, to this double bond, we see the chloride ends up on here, on the least, or on the on this hydrogen on the secondary carbon, and the hydrogen ends up on the one that is the primary position. What the rule typically says is if there are more hydrogens on there, it will tend to get another one. It depends how you like to think of it, but the major product, the one that we will usually see most of, you usually see both, that's why it says major and minor and not only. The major product is the one where the hydrogen ends up on the end where there were already several hydrogens, and that's because the hydrogen is adding to the double bond, forming a carbocation, and the carbocation will go to the most substituted position. That's really why it happens. If you remember why, you don't have to remember what the rule is. If you remember what the rule is, for the purposes of our exam, you don't have to remember why, but I find it easier to understand why, and then I can remember what the rule is. So if we add to this more substituted double bond, then we can think the carbocation is going to end up at this more substituted position, and it will then be attacked by the anion, and the anion in this case is the chloride anion, and so the Cl ends up on this end. Likewise, even if the less substituted end is already a secondary carbon, but the more substituted end is more substituted, it's a tertiary carbon in this case, then we will still drive most of our reaction to form the carbocation at this tertiary carbon end, and the other end will take the hydrogen. Going back to here, in this particular version, they're getting to the theory over time, or they're getting to the mechanism over time. Let's have a look at this example, though. It's quite interesting. So we've got a double bond over here, and what happens is our methyl group here shifts to the middle, and we end up with a chlorine here instead of the blue one. You can see the blue is replaced with the green of the chlorine, and the methyl group here is moved to the middle. So we end up with a completely different molecule, which should remind us of something. It reminds us of the shift reactions that we have. This is a methyl shift. The shifting reactions that we have if we end up with a carbocation. So if we take our H plus and we add it to this double bond, we will tend to put the plus in the middle here. If it's on the end, it's primary. If it's in the middle here, it's secondary. That's good. So we'll tend to put the plus in the middle here, and if we leave it too long, if the chloride doesn't attack it immediately on the end, it will then react, it will then shift. So there will be a methyl shift from here to here, bringing the positive charge to the end, making it a tertiary carbocation, which is much more stable, and that can then react. So it's a rearrangement reaction of the carbocation to make the lowest energy carbocation, and then it reacts with the chloride ion. They're probably going to tell us that on the next page. Let's have a look. So that you just see that. So this is the mechanism. I've already explained that. So the mechanism is that the hydrogen adds first. Whoops, where are we? No, it's all just recapping at the moment. Here's the mechanism. Oops. So the mechanism is that we are going to take our electron-rich electron cloud and attack our hydrogen and give the most electron-rich things the positive charge. So our pushing of electrons comes from this end, pushing electrons into this end, and that causes the bond to flip out in this direction. And then, once we form the carbocation, it can be attacked. So it explains two of the things that we've already seen. It doesn't explain why the bromination happens, and it doesn't explain why the hydrogenation happens all on opposite sides and on one side. But it does explain why an HCl or an HBr will tend to attack so that the hydrogen ends up on this end that already has lots of hydrogens. It's because the carbocation ends up on the most substituted position. So, what else can we have? Nice, we've got a picture of arrows and something better coming. Let's see what we can do. We can draw our arrows. Okay, that's good. The arrow comes from the middle of the bond and attacks our hydrogen. And it's good if we draw it away from the position where the positive charge is going to end up. That's very good, because then it really describes the reaction better. Okay, I hadn't read this one through beforehand, but it's a way of making life a bit neater. I didn't actually know this because I didn't do organic chemistry after university. So this is a way to draw it better, so that we can be sure what's going on, so that we can be sure what we're claiming is going on. Either a bouncy arrow that says all of the electron density ends up on this carbon and then goes out. It's not realistic, but it is at least telling us exactly what's going on. We're going to end up with a, oops, I pointed then, we're going to end up with a bond from here to this hydrogen. This one is probably nicer in that the dashed line denotes where the bond is going to form, and so we can attack with our double bond onto here, and that is not ambiguous at all. So it tells us exactly what's going to happen. We're going to end up with a bond between this hydrogen, with this carbon, sorry, and this hydrogen. And obviously that will break the double bond, and it will make a single bond there, and the positive charge ends up at the only place that it can end up, which is up here. Good. So this is our, it's going to tell us the same thing again, forming a carbocation intermediate being attacked again from the other side, and that gives us our Markovnikov typically. And if we do that with hydration, we will get the same product. So they're just saying, if we do it with an acid, then we will acidify, we'll attack with an H+, that's the electrophile. It's an electrophilic reaction, so the electrophile happens first, and that will give us exactly the same result, that the OH ends up on the position where our halogen was ending up before. But that isn't always what has to happen, because we can find other reaction mechanisms that go over a different step, or an extra step. So as it says here, there's no preference for syn or anti-products. We know we can get those, we know that those happen, but this hasn't yet explained why they happen. But it does explain why our hydrogen tends to end up on the end, and it also explains why we might get rearrangement and where the other bond goes to. Why we might end up with a lot of products if we're not careful. So I've jumped over the next page, actually possibly 2 pages, because it talks about why rearrangement happens. And it had a little bit of background about rearrangement. You can read through that so that you've got it from a different angle, but I won't read it out to you because you can look it up on the internet. What I'm more interested in today is the bromination and maybe some other reactions. So if we're going to add bromine to it, what do they say about it? We know that they attack, or they end up on opposite sides. So that's what they're saying here. And we know that if, what are they saying? Okay, if we have a cis or a trans starting reagent, we end up with different products. So it matters. Something is happening. So what that tells us is there is no carbocation, because the carbocation would remove the information of the chiral centers. So continuing on, we have our reaction and we see results. That's how they're building their logic up anyway. And they're saying, because we only make some of the possible compounds, the formation of a carbocation is impossible, or isn't very likely, because then we would see attack from both sides, so we would see all four possible products. So something unusual is happening. Also, rearrangements don't happen, which we would expect if we form a carbocation. We almost always see rearrangements under some conditions. So here's an example where you would expect this group to focus rearrangement, because it's a very substituted group and it's next door. So if we attack this double bond and made a positive charge on one of these carbons, it would tend to get jumped to here, and it would tend to move one of these methyl groups. That never happens, which suggests we don't go through a carbocation again. And then if we change the solvent, we can change the reaction product, so then we are doing something that looks like we're in the second step attacking with the solvent instead of with the bromine anion. So the second step is fairly simple to imagine. We've got an attack of something to a bromine that's attached, and as I told you, I think it's a three-membered ring because I've looked forward, or because I've taught this before. So let's have a look. This is an example of it. Let's have a look as we go through. So they're recapping again. They do a lot in here. But here is the picture. So we've got our bromine docking onto the top, forming this three-membered ring here, the bromonium ion, and the bromide ion attacks the back. And what they say here is important, that it mostly will attack the carbon best able to stabilize charge. So this ion is positively charged, and one of these two carbons will be more positively charged than the other. The positive charge isn't really on the bromine, it's distributed across the three atoms, and one of them may have more than the other. Obviously, if it's symmetrical, that's not the case, but this one would be the one that would be positive if it was a carbocation, and it's the one that gets attacked. We can't tell in this one, but obviously if we do it with water, which is this one, the water attacks the more substituted positive carbon, and we end up with this product. It also says the other enantiomer are not shown, so obviously if the bromine attacks from the other side, it would be pointing down in this step, and the water would attack from the top. So this would be the other way up, but so would the bromine. So it's always opposite because of the triangular intermediate. And then they say, let's prove it. If we look at this chemical, here's a picture of it. It can be found, it was discovered and isolated. Why is this more stable than any of the others? Well, we've got a stable shape. There's a stable shape here. We've got a lot of groups that can donate to it. They're not moving around because they're held by these rings. And it's an iodine. Iodines are particularly big, so they can distribute the charge particularly much. So this is a very, very stable intermediate compared to all of the others. And it's so stable that it can be isolated just. It does say, think about how that could be. I've just told you. If we go further, we can see that there are other possibilities. So first of all, we've got the bromination, which is exactly what we've seen. We've got chlorination as well. So we just swap bromine for chlorine and we get exactly the same thing. We get iodination, and again we get exactly the same thing. And then if we want to do something else, we want to add another reagent that is a nucleophile, in this case it's water. It will then form a Markovnikov product, which means that our second group, the negative group, the electronegative group, goes on where there is more substitution, where the carbocation would be happier, and the first group, which was the positive group, goes on the one which has got the most hydrogens on, or the least substitution, because the most stable positive charge is the one that takes the negative attacking group. The negative attacking group is the OH minus in this case. We can do that with the equivalent with an alcohol and form an ether instead. And we can also do it with the help of a different chemical, this Chloroxenomide, which does exactly the same thing. It forms this triangular ion. If we want to do it with mercury, we also get a triangular ion, and we get exactly the same thing happen. So we form first of all the mercury triangular ion, and then we have to attack it from the back on the most charged group, on the most positive end, which is this one, because it will have the positive charge on it for the largest proportion of the time, because it has this methyl group on, and this one doesn't. That's good, makes all sense. But there's another step, because we now want to get rid of the mercury, and a typical way to do that would be to reduce it. So we are going to attack from the back. There it is. We're going to attack from the back and add a hydrogen. It depends what we do. So in this case, they've got a free radical intermediate, which means that the chirality of this group is lost. But we can also attack it from the back and have an SN2 reaction, and then we would switch the stereochemistry of this side, and so then we would switch this over. This is where I wanted to get. If we have an epoxide, so an oxygen, we can make the same thing, also by adding to a double bond in some cases, and then we will get similar reactions that also occur via attack from the back to the more substituted partner. If we want to look at epoxides, we will see exactly the same thing. And now we finally got to the one that's different. Whoops, I've opened the wrong thing. Finally gets to the one that's different. So if we take a Borohydride, which is an interesting reagent, we will reduce this double bond. So we're going to add hydride to it. But we tend to end up with hydrogen added to the carbon with the fewest attached hydrogens. So it goes strangely the wrong way round. So something new is happening. It's not agreeing with what we've seen so far. So therefore, we would expect some kind of alternative mechanism. So looking at boration, this is the one that is different. It appears to be different from the results, but again, it's doing something very similarly. The boron is being attacked by the bond, making the positive charge on the place where it's most likely to go, so that would be the most substituted one. That's exactly here. But because the hydrogen comes from the same molecule, it's coming from the same side, we end up with this weird four-membered intermediate. Actually, four-membered intermediates are slightly more likely than three-membered intermediates, but in this case, this particular reaction, the three-membered intermediates are quite common. In this case, we're going to attack the more negative carbon. So our boron will sit closer to the more negative carbon. One of the hydrogens will happen to be close, and we can then rearrange this so that it can break and form a boron molecule on the less substituted carbon, and the hydrogen goes onto the more substituted carbon, which is the opposite of what we had before, because of the way that the mechanism goes. So the positively charged thing is still going onto the correct side. It's going onto the less substituted side, but the positively charged thing will now be replaced with an OH, so it appears to be anti-Markovnikov. Why? Because then we go to the next stage. Whoops, it's okay, I'll get there in a moment. When we get to the next stage, water will attack this with a normal SN2 and knock it off, and so we will end up with our OH on this carbon and not on this one, which is what we would have expected from Markovnikov's rules. But from the mechanism, it still makes sense, which is another reason why I prefer to think about the mechanism than to think about the rules. Here is their explanation. So their explanation is similar. It's saying in the normal Markovnikov reactions, the hydrogen is behaving as the positive species, and the positive species always ends up on the less substituted end. In the boron case, the boron is slightly positive compared to the hydrogen. It's one of the interesting reagents that behaves as a hydride, as an H- donor. So if we use it for other types of chemistry, it's behaving very often as an H- donor, and that means that the boron does the job that the hydrogen would normally do and ends up on this end. And then when we do the oxidation of it, we're going to remove this and take it off. And as they show, I totally messed that up. This is not an SN2 reaction at all. It's oxidation of the boron, and it involves transfer of this bond here down between the carbon and the boron to the oxygen. So if we look at this key rearrangement step, this is what happens. They've drawn the arrow the wrong way round, I see. So this bond goes out this way, so because otherwise it would be doing the wrong thing. So according to their own logic, they should have drawn a dotted line up here. The electrons from this bond end up between the oxygen and the carbon. Bad author, but not as bad as me for not knowing this. And then the hydroxide group is lost, which gets rid of the negative charge. And then we need to get rid of the boron part, which will happen with the base. So let's have a look at that. We're going to take some base, the base will attack it, and this bond will become a lone pair on the oxygen, and it will grab maybe a proton from somewhere to become OH. On their final page, they have a few more confusing reactions, but that are very, very similar. Let us have a quick look at them. So this is our hydroboration. You can see that there's a theme coming up, which is a concerted mechanism, which means that these electrons move all around at pretty much the same time. It's not one after another. It's all going at the same time. And then we end up with the product. In the addition of hydrogen across an alkene, we're adding a hydrogen that's attached to the metal onto the alkene at pretty much the same time. So they're added from one face. And it's obviously got to be quickly enough that the atom can't flip over, or the molecule, sorry, can't flip over in that time. If we're going to make a peroxide, which is what we mentioned before, the peroxide is this group here with an oxygen in the triangle, and that is the finished product. It's reasonably stable. We can collect it, we can use it for things, we can ship it to people, do the reaction. It's the thing that is in damn it. Sorry, I got confused. This is an epoxide, which is an epoxy adhesive. It says it on there. I don't know why I got it mixed up. It's possibly because the other reagent is a peroxy acid. So peroxy is where we've got oxygens one after another in a chain, 2 oxygens. So this is our 2 oxygens in a chain. This is the rest of the acid. So this is the double bond O part of the acid. This is OO, and then the H would normally be sitting over here. It's the acidic hydrogen. And that comes along to our double bond and interacts with it. And the double bond, this new intermediate, can collapse. The hydrogen is effectively transferred from this oxygen to this other oxygen, and this oxygen is transferred from the acid group to the double bond. So this is going to collapse, it's going to become the double bond. This bond comes out here, this bond goes down here, and this bond goes up here. So it's all going round in a circle. It's a cyclic movement of electrons. As one goes in, the next one has to get kicked out. So let's start here again. This double bond, for example, as this, no, it's not a double bond, as this single bond breaks and goes in here to become the double bond, it's got to kick this double bond out, which goes over here to attach to the hydrogen, which allows this one to let go, and it goes in here, which kicks out the double bond up to here, which also would go round and round and round. So it can collapse all in one go and leave as these 2 products. It's a relatively common theme in organic chemistry that we either have multi-step reactions or we have a concerted reaction where all of the electrons move at once because they have to go one after another. This is another funky example with osmium tetroxide. We're not going to talk about this one much, but let's have a look at the intermediate because it's similar to all of the others, but now we've got 5 atoms in our cyclic compound. So we've got our osmium, we've got 2 oxygens, and then we've got the double bond. So this is our transition state, and as we go out, we flip this up to here, this double bond goes across to here, and this one drops down to here, and then we end up with our new state, and we need to get it off. So this is our new state. Then to get our osmium off, we'd have to hydrolyze it with water, so we need water to add to both sides of this, across this bond here effectively, and this bond here, and then we end up with what they call a vicinal diol, so they're on the same side and it's a diol. This is a carbon version, which also has a carbon in the middle, so it's equivalent to the epoxide, but it's got these funky zinc iodide parts in it, and it also does the same thing, that it comes along and it reacts in a little cyclic transition state, but also kicks out and around the other side as well, just like the first example, the epoxide one. Is that the same one? This is much the same, and then we're also going to end up with a carbon with 2 chlorines on it, so we end up with a theme